In this video, we discuss the method of reduction of order. Reduction of order is going to allow us to solve problems like these. We're going to be given a solution y1 of this differential equation, and we'll be asked to find the general solution of this second order linear homogeneous differential equation. The question is, how do you find that general solution? Well, if you have a first solution, you can use that to find the second solution, given what we know about the form of the solution of this equation. Since it's a homogeneous linear second order differential equation, we know that the general solution has the following form. Y equals C1y1 plus C2y2, where y1 and y2 form a linearly independent set of solutions. So we know this, and we already know what y1 is. So the only piece missing is y2. If we could find y2, then we would have enough to write down this solution. If I have y1 and I can find y2, I would just multiply those guys by constants and add them together, and I would get the general solution. The question is, how do you find y2? Well, finding y2 isn't that difficult at all, because we know that y1 and y2 must be linearly independent. So that means that y2 must be some function of x times y1, where that function of x is not equal to a constant. And if you're saying to yourself, how do you know that's true? Well, remember what it would mean for two functions to be linearly dependent. Y1 and y2 would be linearly dependent if y2 was just a constant times y1. If they're linearly independent, y2 must be some function of x times y1, where that function of x is not equal to a constant, because if it were a constant, they would be linearly dependent. Does that make sense? I hope it does. If not, just watch this video again. So we know that y2 has to have this form because y1 and y2 are linearly independent from each other. Now I know what y1 is. I don't know what u is, but if I can find the value of u, then I will know what y2 is. And if I know what y2 is, I can construct the general solution. So the idea of the method is this. We're going to let y2 equal some non-constant function times y1, and we're going to let that be a second linearly independent solution of the differential equation. And then we're going to say, okay, if that's true, what does u have to be? So we're making this assumption. And then since we are assuming that y2 is a second linearly independent solution, and we know that y2 is out there because we know that the general solution has this form, then what does u have to be? So what we'll do in order to find the value of u is we will compute the first and second derivative of y2. You're going to substitute those into the differential equation. And from there, what you'll see is that the resulting simplified equation will be linear, and it'll be linear not in u, but it'll be linear in u prime. So typically at this point, we let w equal u prime, And then you'll have a first order linear differential equation in W. That's why this is called reduction of order. It takes that second order differential equation that we started with and through a substitution makes it a first order linear equation. Then you solve the linear differential equation in W. You're solving that for W. And then once you're done with that, you're going to back substitute. Because W is just something that we made up so that we could solve the differential equation. W is actually equal to U prime from that initial assumption. Now, if you want to get U by itself, and that's what we want U so that we can find Y2, we will anti-differentiate both sides. And then we're going to make appropriate choices for constants, and we'll talk about that when we get there in a specific example. And then we're going to have U. We'll have U by itself. And then once we have U, then Y2 is U times Y1. We can simplify that. And then the general solution is given by this, y equals C1Y1 plus C2Y2. Now I know that that looks like a lot, but if you just think about what it is you're doing and why, I think it makes sense. Everything flows from this initial assumption. We're assuming that Y2 is a second solution to the differential equation and it's U times Y1 where U is not a constant. U can't be a constant because these functions have to be linearly independent from each other. Then you're saying, okay, I've assumed that Y2 is a solution, therefore I can take the derivative of this twice and I can substitute into the differential equation. And since it's a solution, it'll satisfy the differential equation. So we're going to get something over here and that's going to equal 0 because we've assumed that Y2 is a solution. Every time you do that, the simplified equation will be linear in U prime. You will let W equal U prime. And then you're going to solve the linear differential equation in W, you back substitute, you anti-differentiate to get U by itself. And then once you have U, Y2 is U times Y1, and the general solution is C1Y1 plus C2Y2. So it's really making this substitution, which results in the linear equation that we can solve using the integrating factor method, which we've already learned when we studied first order differential equations. Then we back substitute and we anti-differentiate. And then you have to back substitute again to find Y2 and then use Y2 to construct the general solution. There's a lot to this, but the outline I think is pretty simple. It's just substitute, it becomes linear, solve the linear equation, back substitute, anti-differentiate to get U by itself. And then once you have U, you can find Y2 and so on. Okay, so that's the outline of the method. Let me give you a concrete example. We already looked at this differential equation. We had 3t squared times y double prime minus 2t times y prime minus 2 times y equals 0. And I believe that y1 equals t squared is a solution to this differential equation. First, let's verify. Let's check, just in case. Well, if y1 equals t squared, y1 prime is 2t, and y1 double prime is just 2. So we'll have 3t squared times y double prime minus 2t times y prime minus 2 times y equals 0. And we substitute these guys into the differential equation. Y sub 1 double prime was 2, y sub 1 prime was 2t, and y sub 1 itself was t squared. I guess we're checking to see if that's equal to 0, so I shouldn't say that it equals 0 yet. Let's simplify this left-hand side. We've got 6t squared minus 4t squared minus 2t squared. Yep, that's definitely 0. So that allows us to verify that y sub 1 equals t squared is a solution. Okay, so we have this differential equation, and we know that we have this one solution. Now, let's say we want to use reduction of order to find a second linearly independent solution, y2, and use it to construct the general solution. Okay, so we're going to let y2 equal u times y1, which in this case is u times t squared, be a solution to the differential equation. We're assuming that that's a solution where u is not equal to the constant function or a constant function. Because if u were constant, then y2 would just be a constant multiple of t squared, and that would not be linearly independent. So we're saying that this is true. U is some function of t, and it explicitly depends on t. The question is, what is that function of t? If I can find that, then I have y2, and when I have y2, I can find the general solution. Okay, so we've made our assumption. Next, you want to compute the first and second derivative of y2 and substitute into the differential equation. Okay. So if I want the derivative of y2, now remember, u is a function of t. So this is a function of t times a function of t. So I'll have to use the product rule. That's my first function, and that's my second function. The derivative of y sub 2 is derivative of the first times the second plus the derivative of the second times the first. And then if I want the second derivative, I'm going to have to use the product rule again, where this is my first function and this is my second function. And then where this is my first function and that's my second function, I'm going to have to use it twice. So we'll say derivative of the first times the second plus derivative of the second times the first. That's what we have from there, plus, and then over here we've got derivative of the first times the second plus derivative of the second times the first. And then if you have any like terms, it's good to simplify them. I've got 2t times u prime here and another 2t times u prime there. So I actually have 4t times u prime. Now, if y sub 2 is a solution, we can substitute it into the differential equation and it will satisfy that differential equation. So I'll write down my differential equation. It was 3t squared y double prime minus 2t times y prime minus 2 times y equals 0. And we're assuming that y sub 2 is a solution. So when I substitute in y sub 2, I should get 0. So that means we're going to have 3t squared times y sub 2 double prime, which is this. You almost want to write your, or turn your paper so it's in kind of landscape mode. Then we've got minus 2t times y sub 2 prime, which is that. Minus 2 times y sub 2, which is u times t squared. And all of that is equal to 0. And at this point, after you substitute into the differential equation, you want to simplify. And when you do, all of the u terms should cancel out because this will be linear in u prime. So let's simplify. I've got 3t squared times t squared is going to be 3t to the 4th times u double prime. I have to distribute to all three of those terms. Then we'll have 12t cubed times u prime. And then 3t squared times 2u is plus 6t squared times u. Minus, distribute that negative 2t there, minus 2t cubed u prime. Minus 2 times 2 is going to be 4, t times t is t squared. times u minus 2t squared times u equals 0. Now, because y sub 1 is a solution to the differential equation, that's why all of the u terms will cancel. So I've got a 6t squared here, minus a 4t squared times u here, minus a 2t squared times u over here. So 6t squared minus 4t squared minus 2t squared is 0. And if we had done this in general for just a u times y1, we would see that the u times y1 terms that would, well, anyway, these are all canceling out because y1 is a solution. We can prove that, we can justify it in general, but I think it's easier to look at a concrete example. So let's just focus on this concrete example for right now. And let's simplify this further. I've got 12t cubed times u prime here, minus 2t cubed times u prime. So that's 10t cubed times u prime, and that's equal to 0. And then I want the u double prime by itself, so I will divide everything by 3t to the 4th. Okay, that's going to reduce with almost all of those, and of course 0 divided by anything is 0. So we end up with this. So I've got 10 over 3 times 1 over t times u prime here equals 0. Notice that this is linear in u prime. And I'll make a note on the side here as well. All t's will reduce. And this is linear in u prime. Now, some students choose not to substitute, but I find that most of my students prefer to substitute because they aren't used to seeing a linear differential equation with a second derivative in it. So let's just let w equal u prime, and then we'll write this as a linear differential equation in w. If we let w equal u prime, then w prime is the derivative of that, that's u double prime. And then the differential equation can be written this way. We've got u double prime, which is the same as w prime, plus 10 over 3 times 1 over t times u prime, which was w, and that's equal to 0. And now we've got a linear differential equation in w. Now this one happens to be separable because that right-hand side is 0. So if you prefer, you could separate the variables here and you could use that to solve for w of t and then back substitute. It's probably actually easier to solve this separable differential equation than to use the integrating factor method. But I'm going to use the integrating factor method here because in general, that right-hand side isn't 0. And in that case, this wouldn't be separable and you'd have to use the integrating factor method anyway. So I want us to practice using that method because it applies so often. But know that you're just trying to solve this differential equation, and if it's separable, you can go ahead and solve it using that method. That's totally fine. Okay, now let's look at finishing this problem by solving that linear differential equation in W. Okay, so to do that, we've got this. We will identify P of t. P of t is the function in front of the W there after W prime is written with a coefficient of 1. And then you want to anti-differentiate that. And then for reasons that we talked about when we solved linear differential equations, this constant is going to be 0. I guess it's not going to 0. I guess I should just say that I'm choosing it to be 0. So maybe that little arrow there is misleading. I don't think I'll do that anymore. So we are solving for W by identifying P. And then we're computing its antiderivative. Then we define the integrating factor to be e to that power. Now remember, if you've got a number in front of that log, you can use this fact. If you have a constant times natural log of a, you can bring that number inside and you can make it a power for a. So that's natural log of a to the nth power. So that's what I would use here, because right now the log and the exponential don't cancel. They don't cancel until you've got a coefficient of 1 there. So you've got to bring that inside. This is e to the natural log of the absolute value of t to the 10⁻³ power. And now those undo each other. And so you've got t to the 10⁻³ power on some interval. Well, natural log of 0 is not well defined, so this is equal to this as long as t is not equal to 0. Okay, so now you've got your integrating factor for this differential equation, which I've labeled dE star. So I'm going to take dE star and I'm going to multiply it by my integrating factor. So I have w prime plus 10/3 times t times w equals 0. And I'm multiplying everything by t to the 10⁻³ power. And then when you simplify this, well, actually, I'll just write it this way. We'll have t to the 10⁻³ times w prime plus t goes into this once, so that'll become a 7/3. This will be 10⁻³ times t to the 7/3 times w, and 0 times any function is 0. So those are the same. And I don't like the way that looks, so I'm going to use whiteout now. I think I need new whiteout. It's been very transparent lately. There we go. Okay, so this is equivalent to this. And then remember, whenever you're solving a linear ordinary differential equation using an integrating factor, after you multiply by that integrating factor, the left-hand side will always be, if you've done everything correctly, it will always be the derivative with respect to t of that dependent variable times the integrating factor. So we will recognize that the left-hand side is equal to the derivative with respect to t of w times the integrating factor. And now you're just a couple of steps away from isolating w. We've got the derivative of this product equals 0. To get rid of the derivative, we anti-differentiate both sides with respect to t, so don't forget the dt's on both sides. And the antiderivative of the derivative is the original function. So you've got w times t to the 10⁻³ equals the antiderivative of 0, which is just a constant. So this was equivalent to this, and then we anti-differentiated both sides and we got that. Just undoing that differentiation with anti-differentiation, and then we'll divide by the integrating factor to isolate w. So w is equal to this, some constant times t to the negative 10⁻³ if you bring that up to the numerator. Okay, now remember, w is just something we made up so that we could solve the differential equation. way back here, we said that W was equal to U prime. And we're really trying to find U because if I have U times, if I have U, then I can take U and multiply it by Y1 to get Y2. So that's where we're going. So we have to back substitute because we're trying to find U. W was equal to U prime. Remember? That was our substitution. And now to get U by itself, we'll anti-differentiate both sides with respect to t. The antiderivative of the derivative is the original function. And so we'll have this constant, and then we will add 1 to the exponent here. So that's adding 3 over 3. It's giving us negative 7 over 3. And then we're dividing by the new exponent. Dividing by negative 7 over 3 is multiplying by negative 3 over 7. And then we'll add a constant of integration. Since I'm using C here, I'll use C2. I think we used C1 for something else, and now this is C2. Okay, now think about where we're going with this. We just found U by anti-differentiating. But what we want is the simplest U possible so that U times Y1 is a second linearly independent solution of the differential equation. Because remember, eventually we're going here. I don't know if I've got it written down anywhere. Well, actually, I don't have it written down. Oh, here it is. Eventually we're going here. So we have a constant times Y1 in the solution, and then we want to add a constant times Y2 to that solution. So this piece is already going to be there. So we're going to have a generic constant times Y1 already. And we want a generic constant times Y2, and we don't want Y2 to have any constants in it. We don't want a constant times Y2 here, like a constant and then a function, because that constant times that constant would just give me a different constant. So we want to simplify Y2 as much as possible so that it's just a very simple function without any arbitrary constants in it. So this is my U of t. I'm going to take this and multiply by Y1, but if I take this quantity and I multiply by Y1, then I'd have this constant times Y1 as part of my Y2. And I don't need a constant times Y1 as part of Y2 because I will already have a constant times Y1 in the general solution. So let's choose C2 to equal 0 because I don't need that constant times Y2 as part of my U2. Now I want this coefficient out front to be as simple as possible. So I'm just going to choose the value of C so that that coefficient is equal to 1. So we'll choose C to be negative 7 over 3. If I take negative 3 and I multiply it by negative 7 over 3, the negatives cancel and then we'll have 7 over 7 and we just get a 1 out front. So if we make these choices, that tells us that our U of t is equal to t to the negative 7/3. And once we know what U is, I'm spilling my white out over here on my table. I want to pick that up. So we're choosing C2 equals 0, and we want to choose C so that the coefficient of that t to the negative 7/3 is 1. And now you've got U of t. Then you can use U to construct Y2. Remember, Y2 was U times Y1. So that's t to the negative 7/3 times Y1, and Y1 was t squared. And if we multiply those together, if we want to multiply those together, we just add the exponents. So it's negative 7 over 3 plus 6 over 3, which is negative 1 over 3. That's Y2. And then the general solution from there is Y equals C1Y1 plus C2Y2, which is C1 times t squared plus C2 times t to the negative 1/3. This is going to be an issue. We're going to have a problem here when t equals 0, because remember that's actually 1 over t to the 1/3. And we can take the cube root of 0, but we can't divide by 0. That negative exponent means that that's in the denominator. So the interval of existence for this could be one of two intervals. It's just any interval that does not include t equals 0. So you could use 0 to infinity, or you could use negative infinity to 0. If we had an initial condition, like if I knew that t of 1 was equal to something, I would pick the interval that contains t equals 1. And I would actually find the values of those c's as well if I had initial conditions. So we've got y2 here, and then the general solution is y equals c1y1 plus c2y2. Okay, so that's our method. Let's go over it again just briefly now that we've got this concrete example. Let's start at the beginning. So we know that y equals t squared is a solution of this differential equation, and we're trying to find the general solution of this differential equation. So we let y2 equal u times y1. Then since y2 is assumed to be a solution, if we take this first and second derivative and we substitute into the differential equation, because it's assumed to be a solution, we're guaranteed to get a 0. So we'll distribute, we'll simplify where we can, and we'll get this. Now, after simplification, we'll see that all the u's are gone because y1 was a solution. That's a consequence of y1 being a solution. And we'll end up with a differential equation that's linear and u prime. Then I would let w equal u prime so that it's really obvious that the differential equation is equivalent to this. That's u double prime is w prime, u prime is w. Now we've got a linear differential equation on u. So we solve that using the integrating factor method. So we identify p, we anti-differentiate e to the integral of p of t power for that c equal to 0. Gives us that integrating factor. Take the linear differential equation in w and multiply by the integrating factor and simplify, and you'll get this. Now, if you've done everything correctly, this left-hand side should be the derivative with respect to t of w times the integrating factor. Now, I don't know if we checked this when we did this earlier. Let's check. I've got a product. This is a function of t times a function of t. According to the product rule, I should get the derivative of the first times the second. That's right there. That's good. Plus derivative of the second times the first. And the derivative of the second is 10 over 3 times t to the 1 less power. 10 over 3 minus 3 over 3 is 7 over 3. So that's the derivative of the second, and then we multiply by the first. And so that's what we have there. So we've got this derivative of this equals 0. If we want to get rid of the derivative, we take the antiderivative. If we want to get rid of this multiplication, we divide. So that gives us w. We get it by itself. And then we say, okay, w is something we made up so that we could find u. So we back substitute to try to get back to u. W is u prime. We're trying to get rid of a derivative again, so we take the antiderivative of both sides with respect to t, and then we get this. And then we say, okay, we're going to multiply this by y1, and we want y2 to be as simple as possible. Since we're multiplying this by y1, we don't need that c2. We don't need a constant times y1 as a part of our y2. So we'll let this c be 0. And we don't want to take this function, this coefficient, and multiply it by a different c. If we did this u1 or u times y1 there as our y2, and then we multiplied that by a second constant, we'd have like c2 times this other constant times that. Like we want this to be as simple as possible. So we choose this constant to be 0, and we choose this constant in such a way that this leading coefficient is 1. So I just took the reciprocal of that negative 3 over 7, giving me the negative 7 over 3. And now that coefficient is 1. So u is t to that power. And now that I know what u is, I know that y2 is u times y1. Substitute, simplify. And then once you've got y2, the general solution is c1y1 plus c2y2. And then you need to find the interval of existence by looking through the method and thinking about the values of t where this is well defined and where every step in the method actually makes sense. So again, this is our method for solving differential equations using reduction of order. I will solve another problem for you in the next video. I'll see you then.